Okay, let's unpack this paper we're diving into today. Vibe coding, the engineering of managing coding agents.
Yeah, and it's important to say right off the bat, if you're thinking this is just, fancier auto-completion.
Right. Think again.
Exactly. This is way beyond that. It's proposing a whole systematic engineering methodology.
For putting LLMs into the entire software development lifecycle. Not just code gen, but managing the whole thing reliably.
Precisely. And the core idea, the thing they really build on, is this concept of a triadic collaboration.
Triadic, okay, what's involved?
You've got the human developer, you've got the software project itself, the context, basically, and then the coding agent, powered by the LLM.
And the human role changes quite a bit, doesn't it?
Fundamentally. You shift from primarily writing the code yourself to being more of an intent articulator, setting the goals, the vision, and a quality arbiter.
So guiding and reviewing, less driving, more navigating, like you said in the pre-read.
That's a good way to put it. You're steering the ship.
And this whole thing rests on, what, 4 main architectural pillars?
Yeah, they lay out 4 key areas. First, the foundation, the LLMs themselves. Then, how the coding agents are actually architected. Third, the dev environments they need to run safely.
Okay.
And fourth, crucially, the feedback mechanisms. That's how the loop closes.
Got it. And that structure supports 5 specific development models or workflows.
Exactly. 5 models that kind of map to different needs. There's unconstrained automation, UAM for super rapid prototyping.
Quick and dirty.
Pretty much. Then iterative conversational collaboration, ICCM, that's more like pair programming with an AI.
Okay, I can picture that.
Plus, there's a planning-driven model, PDM, for architecture-first stuff. A test-driven model, TDM, using tests as the spec.
Makes sense.
And finally, the context-enhanced model, CEM, which is sort of a layer that helps with large code bases.
Okay, quite a bit to cover. So our mission today is really to get under the hood, right? Look at the LLM techniques, how these agents actually work, how they plan and act.
And the feedback, definitely. How does that loop function? Plus, we absolutely need to talk about the risks, because moving this fast, well, it creates new challenges, especially around security.
All right, let's dive in. The paper gets formal pretty quickly with V, E, A, H, P, E, A. How do we translate that from math symbols into something, practical for engineering?
Right. It looks abstract, but the key is they frame it as a constrained Markov decision process, a constrained MDP.
Okay, MDP. Help me out there.
So basically, it means the human H is the one defining the goals. What does good look like? That's the reward function, the RH dollars. It's your judgment call.
My intent and my quality bar.
Exactly. And the project context, P, sets the boundaries. It defines the state space, what the agent can actually work with.
And that project context P isn't just the code file you have open, is it?
No, definitely not. It's much richer. They break it down into 3 parts. CC code, which is the entire code base.
Oh, yeah?
So databases, schemas, data files, and more, which is all the other stuff, documentation, domain knowledge, maybe even bug tracker info.
So the agent needs access to all of that to be effective.
Absolutely. The quality of its output is directly tied to the quality and completeness of the context it gets.
Which brings us straight to the LLM stack itself. Data seems like the first major consideration. The paper talks about this trade-off between breadth and depth, or maybe breadth and quality.
Yeah, you see different strategies. On one hand, you have sheer scale. Look at the stack V2 67.5 terabytes. Across 600 plus languages. That's massive breadth.
Oh, okay.
But then there's this other push towards maybe not less data overall, but much more curated, high quality data, especially for instruction tuning.
Like Open Code Instruct, that's 5 million samples, right?
Exactly. Or preference data sets like Code Ultra Feedback to really align the model's behavior with what developers actually want.
And this quality over quantity thing seems really important in the fine-tuning stage.
Hugely important. Take supervised fine-tuning, SFT. The paper mentions alpha gases. They got significant gains using just 9,000 really high-quality filtered examples.
Well, and 9,000.
Yeah. It's a big lesson. It's not just about hoarding data, it's about finding the right data. Filtering for gold, as you put it earlier.
Makes sense. So beyond just data, what about the actual training techniques? How are these models learning to understand code, not just spit it out?
Well, you still have your standard autoregressive modeling, like GPT, but for code specifically, masked language modeling, MLM, is really dominant. Think CodeBERT.
Why MLM?
Because it forces the model to look at context both before and after a piece of code bidirectionally. That helps it grasp the structure better. And then there's continual pre-training, CPT.
That's how models stay current, like CodeLlama, DeepSeek Coder.
Exactly. You keep feeding them massive amounts of relevant code data. But the really interesting part is the data mixing.
Mixing, you mean code plus other stuff?
Yeah, like Qwen 2.5 Coder, they found this optimal ratio, something like 7 parts code, 2 parts text, 1 part math data.
And that worked better than just code.
Way better, like sometimes over 20% improvement compared to just training on code alone. Mixing domains seems crucial.
Okay, so that's pre-training and fine-tuning. What about aligning the model afterwards, getting it to behave? We hear about reinforcement learning, PPO.
PPO is kind of the classic baseline, but things are moving fast. DPO, direct preference optimization, is getting really popular because it avoids the complexity of training a separate reward model. It's RL-free.
Simpler, okay.
But for coding, there's something even more targeted. RLVR, reinforcement learning with verifiable rewards.
Verifiable rewards, how does that work?
Well, think about it. Unlike, say, rating the style of a paragraph, code correctness can often be checked automatically. Does it pass the unit tests? Does it compile without errors? Does static analysis flag issues?
So you can get objective yes-no feedback.
Exactly. You get these clear, deterministic reward signals instead of relying on a potentially flawed, learned reward model. That makes RLVR really effective for coding tasks.
Got it. Okay, so we've built the powerful LLM brain. Now, how do we turn that into an agent that can actually do things in a project? What's the architecture?
Right, the agent anatomy. The paper breaks it down into a cognitive system, how it thinks and plans, a memory mechanism, and tool integration.
Let's start with cognition. Planning. Big coding tasks are complex. How does the agent handle that?
It has to break them down. Task decomposition is fundamental. You can't just throw a huge goal like refactor the auth system at an LLM and expect magic. It needs smaller, manageable subtasks.
And how does it figure out those subtasks? We used to just hear about chain of thought, COTE.
COTE is still foundational, yeah. Thinking step by step. But for more complex scenarios, especially in big code bases, agents are using things like tree of thought, TOTI.
Tree of thought.
It explores multiple different lines of reasoning, multiple potential paths or solutions, kind of in parallel before choosing the best one. It's more robust than just a single chain.
So more sophisticated planning.
Definitely. And the planning itself is evolving. It's not just the LLM outlining steps anymore. Now we have LLM as facilitator approaches, where the LLM translates your high-level goal into a formal planning language, like PDDL, that other specialized tools can execute.
But the really cool part seems to be the adaptation, the self-correction. That's reflection, right?
Yes, reflection is a game changer. It adds this explicit self-reflection loop. The agent does something, an evaluator checks the work, like running tests, and if it fails...
Doesn't just try again randomly.
No. A self-reflection module analyzes why it failed, updates its internal clan or knowledge and memory, and then tries again, informed by the failure. It learns.
That sounds powerful. But it must need a good memory system, especially since you mentioned context windows aren't big enough for whole projects.
Absolutely critical. You can't fit gigabytes of code into a, 200K token window? Maybe a million soon, but still not enough.
So how does memory work?
It's typically split. Short-term memory for the immediate back and forth, the current task context, and then long-term memory, usually relying on external vector databases.
Vector DBs for storing embeddings of the code, docs, etc.
Exactly. And the agent needs sophisticated operations on that memory, consolidating new info, indexing it, retrieving the relevant bits when needed, updating things, even forgetting old or irrelevant stuff to stay efficient. It's complex memory management.
Okay, so it can plan, remember, reflect. Now, actually doing things, executing actions, the paper mentions a shift here too, away from just calling predefined tools.
Yeah, this is really interesting. The move is away from rigid, often JSON-based API calls for tools. The trend is towards executable code-based frameworks. Codact is the example they use.
Codact, how's that different?
Instead of just saying, call the file writing tool with these parameters, the LLM generates small snippets of actual code, Python, bash commands, whatever, that perform the action directly within a secure sandbox.
So the action is code.
Right. It unifies everything, file I/O, running commands, internal logic into one dynamic execution space. It makes the agent way more flexible because it can compose and revise actions on the fly rather than being stuck with a fixed set of tools.
That sounds much more powerful.
It is. And we're also seeing multi-agent approaches really shine here, like MapCoder.
MapCoder, what did it do?
It used, I think, 4 specialized agents working together, one for planning, one for coding, one for debugging, etc. And they achieved crazy results like 93.9% pass rate on human eval.
Wow. So dividing the labor among specialized agents works better than one giant model trying to do everything.
It seems that way, yeah. Specialization wins.
Okay, but letting these powerful code executing agents run loose sounds dangerous. What about the environment?
Huge consideration. You absolutely need an isolated execution environment. The agent will generate buggy code, potentially even malicious code if compromised.
So sandboxing is key.
Critical. Containerization, Docker, Kubernetes is the baseline. It gives you that OS level isolation, keeps things lightweight and reproducible.
But is that enough?
Often not for really sensitive stuff. So you see deeper security measures too. Things like hardware-assisted isolation, Intel PKRU was mentioned, or using WebAssembly-based runtimes.
Why WebAssembly?
Because it provides a really strict, memory-safe sandbox. You can tightly control what it accesses, file system, network, everything. It ensures the agent can test its code without risk to the host system. Deterministic and secure.
Makes sense.
Yeah.
Okay, shifting to the human side of this vibe coding equation. The interface. How do we actually interact with these agents?
The paper highlights two main ways this is happening. First is the inline suggestion model. Think GitHub Copilot. Fast, low friction, right there in your editor.
Good for quick completions, refactors.
Exactly, quick iteration. The second paradigm is conversational interaction. Think Cursor IDE or the chat panels in Copilot now.
That's more for explaining intent, debugging longer tasks.
Right, you can have a proper dialogue, clarify things, work through multi-step problems, and the key takeaway seems to be that you really need both.
The combination is best.
Yeah. Inline for the quick stuff, conversational for the complex stuff, and having that persistent dialogue history is crucial for the agent to maintain context across those longer interactions.
Okay, interface is covered. Now, the engine that really drives improvement, feedback. You said this closes the loop. How does feedback work in vibe coding?
It's absolutely central. They break it down into 4 categories.
Yeah.
The first 2 are more objective, machine-driven.
All right, what are they?
First, compiler and static analysis feedback. You know, the errors and warnings your tools spit out.
But compiler errors can be pretty cryptic sometimes.
They can be, but LLMs are getting good at interpreting them. The paper mentions models achieving like 69-81% accuracy in figuring out which static analysis warnings are actually important.
Okay, so they can help prioritize. What's the second type?
Execution feedback. Did the code actually run? Did it pass the tests? Unit tests, integration tests, this is concrete verification.
This seems super important.
It is. There are challenges. Like sometimes AI-generated tests aren't reliable, but using execution feedback gives huge performance boosts. They mentioned code T jumping to nearly 66% pass at 1 just by using test results as feedback.
Okay, compiler and execution, what's third?
The third category brings the human squarely back into the loop. Human feedback, specifically through interactive requirement clarification.
Clarification. Why is that so important?
Because LLMs tend to guess when requirements are fuzzy. One study found they just generated code in over 63% of ambiguous situations without asking for clarification.
They just plowed ahead.
Yeah. But when the system is set up to ask clarifying questions, the accuracy boost is enormous. Like a 45.97% average absolute improvement within just 5 back-and-forth interactions.
Wow. So talking to the human is vital for getting it right when things are unclear.
Absolutely proves the human's role in resolving ambiguity early on. And methods like RLAIF and DPO help integrate human preferences more broadly.
Okay, and the fourth feedback type.
This one's really cool. Self-refinement. This is where the agent learns from its own analysis. Frameworks like Self-Refine and especially Reflection that we mentioned earlier.
The agent critiques itself.
Essentially, yes. It generates output, evaluates it against criteria like tests or internal checks, reflects on failures, and improves its next attempt. All without constant human hand-holding.
And this leads to big gains too.
Massive gains. Reflection hitting 91% pass at 1 on human evil. That's largely thanks to this iterative self-correction loop, learning from its own verbal reinforcement.
Incredible. Okay, so all this tech, the LLMs, the agent architecture, the environment, the feedback loops, it all comes together in these 5 development models, the vibe coding taxonomy.
Exactly. And they classify these models based on sort of 3 dimensions: how much human quality control is there, are there structured constraints, and how well is context managed.
Let's walk through them quickly. First, unconstrained automation model, UAM. You said quick and dirty.
Yeah, think rapid application development, but supercharged. Very fast, low barrier to entry. You basically just trust the AI to generate something functional.
Sounds great for whipping up a prototype fast. What's the catch?
The catch is potentially huge technical debt, and worse, security vulnerabilities. Because there's minimal human oversight, the AI just optimizes for getting something working, often ignoring best practices, safety, maintainability.
So definitely not for production code.
Absolutely not. Disposable prototypes only.
Okay, contrast that with Iterative Conversational Collaboration Model, ICCM.
Yeah.
You liken this to pair programming.
Right. Here, the human is the navigator, guiding, reviewing, setting direction. The AI is the driver, churning out the code.
So you get the speed, but with human oversight built in.
Exactly. It balances speed and quality much better. Technical debt is lower because review is happening constantly. The big requirement, though, is developer experience.
The human needs to know what they're doing.
Definitely. If the navigator isn't experienced enough to provide good feedback and direction, the whole thing kind of degrades. It just becomes UAM with extra steps.
Got it. Then we have two models that rely heavily on constraints. First, planning-driven model, PDM, waterfall-like.
Sort of, yeah. PDM is about establishing the structure up front. Humans create detailed architecture docs, design specifications, the blueprint. Then the AI implements against that plan, sequentially.
Why would you use this?
Essential for large, complex systems where you need really strong architectural coherence across many different modules or teams. Ensures everything fits together according to the grand design.
And the other constraint-heavy one, test-driven model, PDM.
This is literally applying test-driven development. You, the human, write the tests first. Those tests become the specification, the precise constraints for the AI.
So the tests define correctness.
Exactly. And what's fascinating here is that the verification is automated. Passing the tests becomes the objective quality gate, potentially replacing a lot of subjective, manual code review.
High confidence in the output, then.
Extremely high. If you need verifiable correctness, think core algorithms. Financial systems TDM offers the strongest assurance.
Makes sense. And the last one, context-enhanced model, CEM, isn't quite a workflow.
Right. CEM is more like a horizontal layer you can add to the other models. It's all about using techniques like a RAG, retrieval augmented generation, and vector indexing.
To do what?
To constantly inject relevant context from the entire project, code base, snippets, documentation, style guides, past issues into the LLM's prompt when it's working on a task.
Ah, so it understands the broader project context, not just the current file.
Precisely. This is critical for tasks like maintenance, large-scale refactoring, or anything involving changes across multiple files. It helps the AI generate code that's consistent with the existing project logic and style. Big performance boost for large code bases.
Okay, synthesizing all this.
Yeah.
It really feels like a major shift in the developer's role. We're moving from syntax masters to orchestrators.
That's a great way to put it. You're operating at a higher level of abstraction. Your core skills become articulating intent clearly, curating the right context for the agent, and reasoning about the system as a whole, rather than getting bogged down in semicolons and boilerplate.
But, and this is a big but, this speed, this automation, it brings new risks. The paper seems quite concerned about security.
Deeply concerned. And the fundamental problem is simple. Human review, our traditional safety net, just can't keep up with the speed and volume of code these systems can generate. Oversight doesn't scale.
So what are the specific systemic risks they highlight?
They point out three big ones. First is cascading errors. Because these agents often work in pipelines, one agent's output feeds the next. A subtle flaw early on can propagate silently.
Like a domino effect.
Exactly. A small error in planning might lead to slightly wrong code, which causes an issue 3 steps later, resulting in a security vulnerability that's almost impossible to trace back manually.
Okay, that's scary. What's the second risk?
Dependency proliferation. Agents, trying to be helpful, might just pull in new libraries or packages to solve a problem, but are those packages trusted? Do they even exist?
Oh.
Yeah, one study they cited found nearly 1/5 of packages suggested by an agent were either hallucinated, didn't exist, or came from untrusted sources. This just massively inflates your attack surface without you even realizing it.
Yikes. Okay, third risk.
This one might be the trickiest. Alignment failures. Agents are optimized for explicit goals, usually textual ones like make the tests pass.
Right.
But they might achieve that goal while violating implicit norms, things like security best practices, maintainability standards, documentation requirements, maybe even ethical considerations. The code works, technically, but it's brittle, insecure, or non-compliant in ways the explicit metrics didn't capture.
So it meets the letter of the law, but not the spirit.
Precisely. It diverges from true developer intent and erodes quality and safety over time.
So wrapping this up, it feels like we're building incredibly powerful tools, but the safety mechanisms are lagging behind.
That's the crux of it. And it leads to a really important, maybe provocative question for you, the listener, to think about. We know from studies that human oversight gets much less effective when the system being overseen significantly surpasses the overseer's capability.
Right. You can't effectively review something you don't fully understand, especially at high speed.
Exactly. And these coding agents are rapidly approaching or maybe even exceeding human capabilities in certain areas. So the question is, how do we ensure our safety constraints, our alignment mechanisms keep pace? How do we scale oversight alongside the scaling of agent autonomy?
What's the path forward there?
The paper suggests it likely involves building safety checks into the generation process itself. Things like multi-agent debate, having agents critique each other's code for safety flaws, and continuous automated monitoring becoming intrinsic parts of the vibe coding cycle, not just an afterthought. We need to make security a property of the generation process, not just something we check for later.
A fundamental shift in how we build secure software in this new AI-driven era.
It has to be.